PostgreSQL, often simply Postgres, is an object-relational database management system with an emphasis on extensibility and standards compliance. As a database server, its primary function is to store data, securely and supporting best practices, and retrieve it later, as requested by other software applications, be it those on the same computer or those running on another computer across a network. It can handle workloads ranging from small single-machine applications to large Internet-facing applications with many concurrent users. Recent versions also provide replication of the database itself for security and scalability. PostgreSQL implements the majority of the SQL 2011 standard, is ACID compliant and transactional, avoiding locking issues using multiversion concurrency control, provides immunity to dirty reads and full serializability. Handles complex SQL queries using many indexing methods that are not available in other databases. Has updateable views and materialized views, triggers, foreign keys. Supports functions and stored procedures, and other expandability, and has a large number of extensions written by third parties. In addition to the possibility of working with the major proprietary and open-source databases, PostgreSQL supports migration from them, by its extensive standard SQL support and available migration tools. And if proprietary extensions had been used, by its extensibility that can emulate many through some built-in and third-party open-source compatibility extensions, such as for Oracle. PostgreSQL is cross-platform and runs on many operating systems including Linux, FreeBSD, Solaris, and Microsoft Windows. Mac OS X, starting with OS X 10.7 Lion, has the server as its standard default database in the Server Edition, and PostgreSQL client tools in the Desktop Edition. The vast majority of Linux distributions have it available in supplied packages. PostgreSQL is developed by the PostgreSQL Global Development Group, a diverse group of many companies and individual contributors. It is free and open-source software, released under the terms of the PostgreSQL license, a permissive free software license. Name: PostgreSQL's developers pronounce it /epush/3zoeqel/. It is abbreviated as Postgres, its original name. Because of ubiquitous support for the SQL standard amongst most relational databases, the community considered changing the name back to Postgres. However, the PostgreSQL core team announced in 2007 that the product would continue to use the name PostgreSQL. The name refers to the project's origins as a post-Angra database, being a development from University Angra DBMS. History: PostgreSQL evolved from the Angra project at the University of California, Berkeley. In 1982, the project leader, Michael Stonebreaker, left Berkeley to make a proprietary version of Angra. He returned to Berkeley in 1985 and started a post-Angra project to address the problems with contemporary database systems that had become increasingly clear during the early 1980s. The new project, Postgres, aimed to add the fewest features needed to completely support types. These features included the ability to define types and to fully describe relationships, something used widely before but maintained entirely by the user. In Postgres, the database understood relationships, and could retrieve information in related tables in a natural way using rules. Postgres used many of the ideas of Angra, but not its code. Starting in 1986, the team published a number of papers describing the basis of the system, and by 1988 had a prototype version. The team released version 1 to a small number of users in June 1989, then version 2 with a rewritten rules system in June 1990. Version 3, released in 1991, again rewrote the rules system, and added support for multiple storage managers and an improved query engine. By 1993 the great number of users began to overwhelm the project with requests for support and features. After releasing version 4 primarily a CLENUPA the project ended. But open-source software developers could obtain copies and develop the system further, because Berkeley had released Postgres under an MIT-style license. In 1994, Berkeley graduate students Andrew Yu and Jolly Chen replaced the Angular-based QUEL query language interpreter with one for the SQL query language, creating Postgres 95. The code was released on the web. In July 1996, Mark Fournier at Hub.org Networking Services provided the first non-university development server for the open-source development effort. Along with Bruce Mormian and Vadim B. Mike Heave, work began to stabilize the code inherited from Berkeley. The first open-source version was released on August 1, 1996. In 1996, the project was renamed to PostgreSQL to reflect its support for SQL. The first PostgreSQL release formed version 6.0 in January 1997. Since then, the software has been maintained by a group of database developers and volunteers around the world, coordinating via the Internet. The PostgreSQL project continues to make major releases and minor bug fix releases, all available under its free and open-source software PostgreSQL license. Code comes from contributions from proprietary vendors, support companies, and open-source programmers at large. Multiversion concurrency control. PostgreSQL manages concurrency through a system known as multiversion concurrency control, which gives each transaction a snapshot of the database, allowing changes to be made without being visible to other transactions until the changes are committed. This largely eliminates the need for read locks, and ensures the database maintains the ACID principles in an efficient manner. PostgreSQL offers 3 levels of transaction isolation: read committed, repeatable read and serializable. Because PostgreSQL is immune to dirty reads, requesting a read uncommitted transaction isolation level provides read committed instead. Prior to PostgreSQL 9.1, requesting serializable provided the same isolation level as repeatable read. PostgreSQL 9.1 and later support full serializability via the serializable snapshot isolation technique. Storage and replication. PostgreSQL, beginning from version 9.0, includes built-in binary replication, based on shipping the changes to slave systems asynchronously. Version 9.0 also introduced the ability to run read-only queries against these replicated slaves, where earlier versions would only allow that after promoting them to be a new master. This allows splitting read traffic among multiple nodes efficiently. Earlier replication software that allowed similar read scaling normally relied on adding replication triggers to the master, introducing additional load onto it. Beginning from version 9.1, PostgreSQL also includes built-in synchronous replication that ensures that, for each write transaction, the master waits until at least one slave node has written the data to its transaction log. Unlike other database systems, the durability of a transaction can be specified per database, per user, per session or even per transaction. This can be useful for workloads that do not require such guarantees, and may not be wanted for all data as it will have some negative effect on performance due to the requirement of the confirmation of the transaction reaching the synchronous standby. There can be a mixture of synchronous and asynchronous standby servers. A list of synchronous standby servers can be specified in the configuration which determines which servers are candidates for synchronous replication. The first in the list which is currently connected and actively streaming is the one that will be used as the current synchronous server. When this fails, it falls to the next in line. Synchronous multi-master replication is currently not included in the PostgreSQL core. PostgreSQL, which is based on PostgreSQL, provides scalable synchronous multi-master replication, available in version 1.1, is licensed under the same license as PostgreSQL. The community has also written some tools to make managing replication clusters easier, such as a repmgr. There are also several asynchronous trigger-based replication packages for PostgreSQL. These remain useful even after introduction of the expanded core capabilities, for situations where binary replication of an entire database cluster is not the appropriate approach. Slonny Longest, part of Sky Tools, Bucado multi-master replication, symmetric DS multi-master, multi-tier replication, indexes. PostgreSQL includes built-in support for regular B-tree and hash indexes, and 2 types of inverted indexes, generalized search trees and generalized inverted indexes. Hash indexes are implemented, but discouraged because they cannot be recovered after a crash or power loss. In addition, user-defined index methods can be created, although this is quite an involved process. Indexes in PostgreSQL also support the following features. Expression indexes can be created with an index of the result of an expression or function, instead of simply the value of a column. Partial indexes, which only index part of a table, can be created by adding a where clause to the end of the createIndex statement. This allows a smaller index to be created. The planner is capable of using multiple indexes together to satisfy complex queries, using temporary and memory bitmap index operations. As of PostgreSQL 9.1, k-nearest neighbors indexing provides efficient searching of closest values to that specified, useful to finding similar words, or close objects or locations with geospatial data. This is achieved without exhaustive matching of values. In PostgreSQL 9.2 and above, index-only scans often allow the system to fetch data from indexes without ever having to access the main table. Schemas. In PostgreSQL, all objects are held within a schema. Schemas effectively act like namespaces, allowing objects of the same name to coexist in the same database. Schemas are analogous to directories in a file system, except that they cannot be nested, nor is it possible to create a symbolic link pointing to another schema or object. By default, databases are created with the public schema, but any additional schemas can be added, and the public schema isn't mandatory. A search path determines the order in which schemas are checked on unqualified objects, which can be configured on a database or role level. The search path, by default, contains the special schema name of $user, which first looks for a schema named after the connected database user. If such a schema is not found, it then proceeds to the next schema. New objects are created in whichever valid schema is listed first in the search path. Data types. A wide variety of native data types are supported, including Boolean, arbitrary precision numerics, character, binary, date time, money, enum, bitstrings, text search type, composite, HSTORE, arrays up to 1 GB in total storage size. Geometric primitives, IPv4 and IPv6 addresses, CIDR blocks and MAC addresses, XML supporting XPATH queries, UUID, JSON. In addition, users can create their own data types which can usually be made fully indexable via PostgreSQL's GIST infrastructure. Examples of these include the Geographic Information System data types from the PostGIS project for PostgreSQL. There is also a data type called a domain, which is the same as any other data type but with optional constraints defined by the creator of that domain. This means any data entered into a column using the domain will have to conform to whichever constraints were defined as part of the domain. Starting with PostgreSQL 9.2, a data type that represents a range of data can be used which are called range types. These can be discrete ranges or continuous ranges. The built-in range types available include ranges of integers, big integers, decimal numbers, timestamps and dates. Custom range types can be created to make new types of ranges available, such as IP address ranges using the INET type as a base, or float ranges using the float data type as a base. Range types support inclusive and exclusive range boundaries using the and characters respectively. Represents all integers starting from and including 4 up to but not including 9. Range types are also compatible with existing operators used to check for overlap, containment, right of etc. User-defined objects. New types of almost all objects inside the database can be created, including casts, conversions, data types, domains, functions, including aggregate functions and window functions, indexes including custom indexes for custom types, operators, procedural languages, inheritance. Tables can be set to inherit their characteristics from a parent table. Data in child tables will appear to exist in the parent tables, unless data is selected from the parent table using the only keyword, that is select from only parent table. Adding a column in the parent table will cause that column to appear in the child table. Inheritance can be used to implement table partitioning, using either triggers or rules to direct inserts to the parent table and to the proper child tables. As of 2010, this feature is not fully supported yet. In particular, table constraints are not currently inheritable. All check constraints and not null constraints on a parent table are automatically inherited by its children. Other types of constraints are not inherited. Inheritance provides a way to map the features of generalization hierarchies depicted in entity relationship diagrams directly into the PostgreSQL database. Other storage features, referential integrity constraints including foreign key constraints, column constraints, and row checks, binary and textual large object storage, table spaces, per-column collation, online backup, point-in-time recovery, implemented using write-ahead logging, in-place upgrades with PG upgrade for less downtime, control and connectivity, foreign data wrappers. As of version 9.1, PostgreSQL can link to other systems to retrieve data via foreign data wrappers. These can take the form of any data source, such as a file system, another ORDBMS, or a web service. This means regular database queries can use these data sources like regular tables, and even join multiple data sources together. Interfaces. PostgreSQL has several interfaces available and is also widely supported among programming language libraries. Built-in interfaces include libpq and ecpg. External interfaces include libpqxx C++ interface, PostgresDAC, PostgresDAC, dbdpg, Perl DBI driver, JDBC, JDBC interface, Lua interface, npgsql, .NET Data Provider, StreetLinks Spatial Kit, Link Tool to ArcGIS, Node Postgres, Node.js interface, PGOLEDB, OLEDB interface, PSQL ODBC, ODBC interface, FSICAP2, Python interface, PGTCLNG, TCL interface, PYODBC, Python library, PHP5 PGSQL, PHP driver based on libpq. Procedural languages. Procedural languages allow developers to extend the database with custom subroutines, often called stored procedures. These functions can be used to build triggers in custom aggregate functions. Procedural languages can also be invoked without defining a function, using the do command at SQL level. Languages are divided into two groups. Safe languages are sandboxed and can be safely used by any user. Procedures written in unsafe languages can only be created by super users, because they allow bypassing the database's security restrictions, but can also access sources external to the database. Some languages like Perl provide both safe and unsafe versions. PostgreSQL has built-in support for 3 procedural languages, plain SQL. Simpler SQL functions can get expanded inline into the calling query, which saves function call overhead and allows the query optimizer to see inside the function. PLPGSQL, which resembles Oracle's PLSQL procedural language, and SQL PSM. Which allows loading custom shared libraries into the database. Functions written in C offer the best performance, but bugs in code can crash and potentially corrupt the database. Most built-in functions are written in C. In addition, PostgreSQL allows procedural languages to be loaded into the database through extensions. 3 language extensions are included with PostgreSQL to support Perl, Python and TCL. There are external projects to add support for many other languages, including Java, JavaScript, R, triggers. Triggers are events triggered by the action of SQL/DML statements. For example, an insert statement might activate a trigger that checks if the values of the statement are valid. Most triggers are only activated by either insert or update statements. Triggers are fully supported and can be attached to tables. In PostgreSQL 9.0 and above, triggers can be per column and conditional, in that update triggers can target specific columns of a table, and triggers can be told to execute under a set of conditions as specified in the triggers where clause. As of PostgreSQL 9.1, triggers can be attached to views by utilizing the instead-of condition. Views in versions prior to 9.1 can have rules, though. multiple triggers are fired in alphabetical order. In addition to calling functions written in the native PL/PostgreSQL, triggers can also invoke functions written in other languages like PL/Python or PL/Perl. Asynchronous notifications. PostgreSQL provides an asynchronous messaging system that is accessed through the notify, listen and unlisten commands. A session can issue a notify command, along with a user-specified channel and an optional payload, to mark a particular event occurring. Other sessions are able to detect these events by issuing a listen command, which can listen to a particular channel. This functionality can be used for a wide variety of purposes, such as letting other sessions know when a table has updated or for separate applications to detect when a particular action has been performed. Such a system prevents the need for continuous polling by applications to see if anything has yet changed, and reducing unnecessary overhead. Notifications are fully transactional, in that messages are not sent until the transaction they were sent from is committed. This eliminates the problem of messages being sent for an action being performed which is then rolled back. Many of the connectors for PostgreSQL provide support for this notification system so it can be used by external applications. Rules allow the query tree of an incoming query to be rewritten. Rules, or more properly, query rewrite rules, are attached to a table class and rewrite the incoming DML into one or more queries that either replace the original DML statement or execute in addition to it. Query rewrite occurs after DML statement parsing, but before query planning. Other querying features: transactions, full text search, views, materialized views, updateable views, recursive views, inner, outer, and cross-joins, subselects, correlated subqueries, regular expressions, common table expressions and writable common table expressions, encrypted connections via SSL. Domains, save points, two-phase commit. Toast is used to transparently store large table attributes in a separate area, with automatic compression. Embedded SQL is implemented using preprocessor. SQL code is first written embedded into C code. Then code is run through ECPG preprocessor, which replaces SQL with calls to code library. Then code can be compiled using a C compiler. Embedding works also with C++, but it does not recognize all C++ constructs. Security within the database is managed on a per-role basis. A role is generally regarded to be a user, or a group. Permissions can be granted or revoked on any object down to the column level, and can also prevent the creation of new objects at the database, schema or table levels. The PostgreSQL extension provides an additional layer of security by integrating with Linux. This utilizes PostgreSQL security label feature. PostgreSQL natively supports a broad number of external authentication mechanisms including password, GSS API, SSPI, Kerberos, ident, peer, LDAP, Active Directory. Radius, certificate, PAM. The GSS API, SSPI, Kerberos, peer, ident and certificate methods can also use a specified map file that lists which users matched by that authentication system are allowed to connect as a specific database user. These methods are specified in the cluster's host-based authentication configuration file, which determines what connections are allowed. This allows control over which user can connect to which database, where they can connect from, which authentication system will be enforced, and whether the connection must use SSL. Upcoming features in 9.4, in order of commit, include, concurrent refresh for materialized views, filter clause for aggregate functions, with check clause for auto-updatable views, with ordinality support, multi-argument unnest, and table syntax, alter system command to change persistent configuration from within database. PGPWM extension to load relation data into the buffer cache of either the OS or PostgreSQL, ordered set aggregates, alter table space, move command for moving objects in bulk between table spaces, replication slots for automatic wall tracking to eliminate replication conflicts, many GIN index enhancements to speed up searching and significantly reduce index size, logical decoding of wall data into logical changes, JSONB data type and related index operator classes, reduced lock levels for ultra-table commands, add-ons, Madlib, an open-source analytics library for PostgreSQL providing mathematical, statistical and machine learning methods for structured and unstructured data, MySQL Migration Wizard, included with Enterprise DB's PostgreSQL installer, Performance Wizard, included with Enterprise DB's PostgreSQL installer, PG routing, extended PostGIS to provide geospatial routing functionality, PostGIS, a popular add-on which provides support for geographic objects, Postgres Enterprise Manager, a non-free tool consisting of a service, multiple agents, and a GUI which provides remote monitoring. Management, reporting, capacity planning and tuning, StreetLinks Spatial Kit, extension for directly connecting to spatial databases, benchmarks and performance. Many informal performance studies of PostgreSQL have been done. Performance improvements aimed at improving scalability started heavily with version 8.1. Simple benchmarks between version 8.0 and version 8.4 showed that the latter was more than 10 times faster on read-only workloads and at least 7.5 times faster on both read and write workloads. The first industry standard and peer-validated benchmark was completed in June 2007 using the Sun Java System Application Server 9.0 Platform Edition, Ultra Spark T1-based Sunfire Server and Postgres 8.2. This result of 778.14 SPEC JAPP Server 2004 JOPS at standard compares favorably with the 874 JOPS at standard with Oracle 10 on an Itanium-based HPUX system. In August 2007, Sun submitted an improved benchmark score of 813.73 SPEC JAPP Server 2004 JOPS at standard. With the system under test at a reduced price, the price performance improved from $84.98 per JOPS to $70.57 per JOPS. The default configuration of PostgreSQL uses only a small amount of dedicated memory for performance-critical purposes such as caching database blocks and sorting. This limitation is primarily because older operating systems required kernel changes to allow allocating large blocks of shared memory. PostgreSQL.org provides advice on basic recommended performance practice in a wiki. In April 2012, Robert Haas of Enterprise DB demonstrated PostgreSQL 9.2's linear CPU scalability using a server with 64 cores. Platforms. PostgreSQL is available for the following operating systems: Linux, Windows, Dragonfly BSD, FreeBSD, OpenBSD, NetBSD, Mac OS X, AIX, BSDOS, HPUX, IRIX, OpenIndiana, OpenSolaris, SCO OpenServer, SCO UnixWare, Solaris and True64 Unix. As of 2012, support for the following obsolete systems was removed: DGUX, NeXTSTEP, Sun OS 4, SVR4, Ultrix4, and Unevil. Most other Unix-like systems should also work. PostgreSQL works on any of the following instruction set architectures: x86 and x86-64 on Windows and other operating systems. Other than Windows, IA64 Itanium, PowerPC, PowerPC 64, S/390, S/390X, SPARC, SPARC 64, Alpha, ARMv8A and older ARM, MIPS, MIPSL, M68K, and PA-RISC. It is also known to work on M32R, NS32K, and VAX. In addition to these, it is possible to build PostgreSQL for an unsupported CPU by disabling spin locks. Database administration. Open source front-ends and tools for administering PostgreSQL include PSQL. The primary front-end for PostgreSQL is the PSQL command line program, which can be used to enter SQL queries directly, or execute them from a file. In addition, PSQL provides a number of meta commands and various shell-like features to facilitate writing scripts and automating a wide variety of tasks. for example tab completion of object names and SQL syntax. pgadmin. The pgadmin package is a free and open-source graphical user interface administration tool for PostgreSQL, which is supported on many computer platforms. The program is available in more than a dozen languages. The first prototype, named PG Manager, was written for PostgreSQL 6.3.2 from 1998, and rewritten and released as pgadmin under the GNU General Public License in later months. The second incarnation was a complete rewrite, first released on January 16, 2002. The third version, pgadmin 3, was originally released under the artistic license and then released under the same license as PostgreSQL. Unlike prior versions that were written in Visual Basic, pgadmin 3 is written in C++, using the WX-Widgets framework allowing it to run on most common operating systems. PHP pgadmin. PHP pgadmin is a web-based administration tool for PostgreSQL written in PHP and based on the popular PHP MyAdmin interface originally written for MySQL administration. PostgreSQL Studio. PostgreSQL Studio allows users to perform essential PostgreSQL database development tasks from a web-based console. PostgreSQL Studio allows users to work with cloud databases without the need to open firewalls. Team PostgreSQL, Ajax JavaScript-driven web interface for PostgreSQL. Allows browsing, maintaining and creating data and database objects via a web browser. The interface offers tabbed SQL editor with auto-completion, row editing widgets, click-through foreign key navigation between rows and tables, favorites management for commonly used scripts, among other features. Supports SSH for both the web interface and the database connections. Installers are available for Windows, Mac and Linux, as well as a simple cross-platform archive that runs from a script. LibreOffice OpenOffice.org base. LibreOffice OpenOffice.org base can be used as a front-end for PostgreSQL. Pgfine. The Pgfine PostgreSQL log analyzer generates detailed reports from a PostgreSQL log file and provides vacuum analysis. A number of companies offer proprietary tools for PostgreSQL. They often consist of a universal core that is adapted for various specific database products. These tools mostly share the administration features with the open-source tools but offer improvements in data modeling, importing, exporting or reporting. Prominent users, prominent organizations and products that use PostgreSQL as the primary database include Yahoo! For web user behavioral analysis, storing 2 petabytes and claimed to be the largest data warehouse using a heavily modified version of PostgreSQL with an entirely different column-based storage engine and different query processing layer. While for performance, storage, and query purposes the database bears little resemblance to PostgreSQL, the front end maintains compatibility so that Yahoo can use many off-the-shelf tools already written to interact with PostgreSQL. In 2009, social networking website MySpace used Aster Data Systems' N-cluster database for data warehousing, which was built on and modified PostgreSQL. State Farm uses PostgreSQL on their Aster Data Systems' N-cluster analytics server. Jenny.com uses PostgreSQL for their main genealogy database. OpenStreetMap, a collaborative project to create a free editable map of the world. Affiliates, domain registries for org, info and others. Sony Online Multiplayer Online Games. BASF, shopping platform for their agribusiness portal. Reddit social news website. Skype VoIP application, central business databases. Sun XVM, Sun's virtualization and data center automation suite. Music Brains, open online music encyclopedia. International Space Station for collecting telemetry data in orbit and replicating it to the ground. My Yearbook social networking site. Instagram, a popular mobile photo sharing service, disks, an online discussion and commenting service. PostgreSQL is offered by some major vendors as software as a service. Heroku, a platform as a service provider, has supported PostgreSQL since the start in 2007. They offer value-add features like full database rollback, which is based on Wall-E, open-source software developed by Heroku. In January 2012, EnterpriseDB released a cloud version of both PostgreSQL and their own proprietary Postgres Plus advanced server with automated provisioning for failover, replication, load balancing, and scaling. It runs on Amazon Web Services. VMware offers vFabric Postgres for private clouds on vSphere since May 2012. In 2013 November, Amazon.com announced that they are adding PostgreSQL to their relational database service offering. Proprietary derivatives and support. Although the license allowed proprietary products based on Postgres, the code did not develop in the proprietary space at first. The first main offshoot originated when Paula Hawthorne and Michael Stonebreaker formed Illustra Information Technologies to make a proprietary product based on Postgres. In 2000, former Red Hat investors created the company Great Bridge to make a proprietary product based on PostgreSQL and compete against proprietary database vendors. Great Bridge sponsored several PostgreSQL developers and donated many resources back to the community, but by late 2001 closed due to tough competition from companies like Red Hat and to poor market conditions. In 2001 Command Prompt, Incorporated released Mammoth PostgreSQL, a proprietary product based on PostgreSQL. In 2008 Command Prompt, Incorporated released the source under the original license. Command Prompt, Incorporated continues to support the PostgreSQL community actively through developer sponsorships and projects including PL-Perl, PL-PHP, and hosting of community projects such as the PostgreSQL Build Farm. In January 2005, PostgreSQL received backing by database vendor Pervasive Software, known for its Retrieve product which was ubiquitous on the Novell NetWare platform. Pervasive announced commercial support and community participation and achieved some success. In July 2006, Pervasive left the PostgreSQL support market. In mid-2005 two other companies announced plans to make proprietary products based on PostgreSQL with focus on separate niche markets. EnterpriseDB added functionality to allow applications written to work with Oracle to be more readily run with PostgreSQL. Greenplum contributed enhancements directed at data warehouse and business intelligence applications, including the Postgres project. In October 2005 John Louis Okono, Executive Vice President of Software at Sun Microsystems, commented, "We're not going to OEM Microsoft but we are looking at PostgreSQL right now," although no specifics were released at that time. By November 2005 Sun had announced support for PostgreSQL. By June 2006 Sun Solaris 10 shipped with PostgreSQL. In August 2007, EnterpriseDB announced EnterpriseDB Postgres, a pre-configured distribution of PostgreSQL including many contrib modules and add-on components. EnterpriseDB Postgres was renamed to Postgres Plus in March 2008. Postgres Plus is available in two versions, Postgres Plus Solution Pack, and Postgres Plus Advanced Server which has all the features of Postgres Plus Solutions Pack plus Oracle compatibility, performance features not available in PostgreSQL, as well as advanced security features not available in PostgreSQL. Both versions are available for download at no cost and are fully supported. The Solution Pack components and Advanced Server are restricted by a limited use license for evaluation purposes only unless purchased through a subscription. In 2011, EnterpriseDB announced Postgres Plus Cloud Database, which easily provisions PostgreSQL and Postgres Plus Advanced Server databases in single instances, high availability clusters, or development sandboxes for database as a service environments. In 2011, 2ND Quadrant became a platinum sponsor of PostgreSQL, in recognition of their long-standing contributions and developer sponsorship. 2ND Quadrant employ one of the largest teams of PostgreSQL contributors and provide professional support for open-source PostgreSQL. Many other companies have used PostgreSQL as the base for their proprietary database projects, for example Treviso, Netezza, Paraxel. In many cases the products have been enhanced so much that the software has been forked, though with some features cherry-picked from later releases. Release history. See also: Comparison of relational database management systems, references. Further reading. External links, official website, PostgreSQL Extension Network, PostgreSQL at DMOZ, Heroku Postgres, Postgres App.